we are going to now extend the discussion of intermolecular forces to look very particularly at water. And then once we've looked at water a little bit more in detail, we're going to look at the formation of solutions and the factors that affect solution formation for both covalent compounds and ionic compounds. So we mentioned last class that water is unique among compounds because of the fact that it participates almost exclusively in hydrogen bonding when it comes to intermolecular forces. There is some debate about this, but really, given that each molecule can, say, participate in about 4 hydrogen bonds, and it's so small, we saw that, even though it has a molar mass of only 18 grams per mole, it has an incredibly high boiling point relative to other molecules, even when you account for molar mass, especially when you account for molar mass. So this unique structural feature of water and then how it relates to other water molecules and then other molecules in general mean that we see some unique physical properties. So the first one that I want to talk about, and I did mention it briefly last class, is the high surface tension of water. So remember, surface tension is basically kind of essentially the energy required to break the surface of a water of water when you pass through. But one of the things we notice with water, for example, is that it beads, right? When it's hanging, say, on a spider web or on a freshly waxed car, which we can talk about in a minute. But the reason is surface tension works this way. When we have an interface, so we have water molecules and then air molecules above. Now, the water molecules are strongly attracted to one another by hydrogen bonding. But if we think of these attractions as vectors, there's essentially a net vector towards the center of whatever bit of water that there is. Now, oftentimes gravity gets in the way, but in a little bead like this is why the water molecules kind of pull in towards themselves. Or I don't know if you've ever seen like a picture of an astronaut drinking juice in space, and there's like this glob of water that stays almost spherical, really. Now, this attraction towards the center and towards its neighbors here makes that there is essentially a surface here. And that's why we have things like bugs that can walk on water and so on. Now, so the first thing is water has very high surface tension relative to most other liquids, right? The next feature that I want to talk about is the weird kind of thing about the density of water. So for nearly all substances, I won't say all other substances, but for many other substances, the majority, density and physical state follow a neat pattern, which is gases are the least dense, right? The particles are super far apart. And then liquids are next, and solids are the most dense. That's the general rule. Water doesn't follow that trend, right? Obviously, gas phase water, steam, is the lowest density. But if we look at the liquid water and the solid water, what we notice is, in fact, that solid water is slightly less dense than liquid water. Now, the reason for this is when we cool something down, right, we slow the movement of the particles down. And then we eventually start to restrict the movement of the particles. And normally what that means is the particles are able to sort of stay closer and closer to each other. The interesting thing with water is that the ideal arrangement of hydrogen bonds and the ideal separation between the molecules by hydrogen bonding is a little bit longer than when they're moving around quickly, right? If you think about in liquid water, you have water molecules that are moving, they make hydrogen bonds, and then now hydrogen bonds with the next molecule as they slide past each other. As things slow down, the hydrogen bonds can actually hold the molecules in whatever arrangement gives the water the strongest hydrogen bonds that can form, because the translational movement of those hydrogen bonds isn't enough to actually break them. So what happens is the water molecules almost snap into place, and the distance that they snap into place is a little bit further apart than when water is in the liquid form. And so we get solid water that is less dense than liquid water. You guys already know this intuitively because when you put ice in a drink, it floats, right? Or you know that when a lake freezes in the winter, there's ice on top. So this is evolutionarily and for life on Earth, this is actually a pretty important feature, because if water were more dense as a solid, what would happen in the winter? So the air would get cold. The water that is closest to the air at the surface, it would freeze. Now, if it was more dense, it would sink. Then the next water at top would freeze and it would sink, and so on. And rivers, lakes, potentially even oceans would freeze solid. That's not what happens. Ice is less dense than liquid water. So what happens is the top layer of ice, of water, freezes into ice. And that actually acts as an insulator to keep water underneath it liquid, and so that living creatures can survive through the winter underneath a lake, which is why, for example, you can go ice fishing. So that's one of the weird things about water. It's very unique. The other thing that we're going to talk about is capillary action. Now, the terminology here sometimes gets a little confusing again for people, but I don't want you to really get too caught up with it. Any of the intermolecular forces that we have talked about can be either adhesive or cohesive. It just depends on the context in which they're acting. So what do these two things mean? So a cohesive force is the force that holds molecules or atoms of one type of compound to itself, right? So for example, in water, that adhesive force the cohesive force is hydrogen bonding. Now, what we've got here is we've got two glass tubes, and in this one here, we've got mercury, and in this one here, we have water. Now, mercury is a metal, and so the cohesive force, the thing that holds mercury atoms to each other, is metallic bonding, which is in the category, in terms of strength, it's in the category with ionic bonding and covalent bonding, so very strong. Now, adhesive forces are forces that get different types of materials to stick to each other. Think of adhesive tape, right? Scotch tape is adhesive tape, gets things to stick. Now, if we look at the mercury and the water, there's some interesting things to note. The first thing is these are equal volumes of mercury and water, I think. That doesn't actually really matter. What is interesting is that this is a pattern that you're used to seeing, right? When you read a burette or you look at the volume of a volumetric flask or a pipette, right? What do we look for? We look for a concave meniscus. Right? That's normal. But if you put mercury in a glass tube, now you guys, we don't have mercury thermometers anymore, but mercury in a glass tube has a convex meniscus. So what's going on? Why is this happening? Now, part of this has to do with the forces. Well, entirely, actually, this has to do with the forces that are at play. Now, glass is silicon dioxide. So glass is, the empirical formula is SiO2 for glass. But it's not individual molecules of SiO2. Glass is what we call a network covalent solid. It's almost like a polymer or a plastic, except that it's not made of carbon. And what that means is that each piece of glass is actually one giant molecule, and it forms an essentially infinite network, as big as the piece of glass, where each silicon atom is connected to 4 other atoms, and they're oxygens. And so on. All right. I'm just going to draw it. that. And sort of something like this. It's not as tidy as this, but sort of it's really a network of, or web even, of silicon and oxygen atoms. And then you'd have your surface of the glass. Now, when mercury atoms come into contact with the glass, well, mercury atoms are nonpolar. So the only type of interaction they can form with the glass are dispersion interactions. We're not making new types of bonds. We're just making new intermolecular forces. So they can either form weak dispersion interactions, right, or strong metallic bonds with each other. And so what happens is the strongest bonds that can form are the ones that are going to form. And so what happens is the mercury atoms squeeze away from each other. They squeeze towards each other away from the sides of the glass. They try to minimize the amount of contact with the glass and maximize the number of metallic bonds. And it creates this convex meniscus that we observe. Now, so in the case of mercury, the cohesive forces are metallic bonding, and the adhesive forces are dispersion. And the cohesive forces are stronger, so they try to minimize this interaction. Now, in the case of water, it's a little bit different because water is held together by hydrogen bonds, right? Now, we know that if I have a hydrogen atom like this, right, it can participate in hydrogen bonds as well. And in fact, it's able to form hydrogen bonds with basically anything else that has lone pairs. So the oxygen here has a lone pair, and so we can form a hydrogen bond between the glass and the water. And it turns out, so just on the sort of straight up basic level, it's hydrogen bonds or hydrogen bonds. So in terms of strength, they're about the same, except that the glass is solid, which means that the atoms in the glass are not moving. They're staying still. They're vibrating, but they're staying still, which means that the water molecule can actually form better hydrogen bonds with the glass than it can with other water molecules. And so what happens is it starts to try and maximize the interactions with the glass, and so it starts to creep up the side. Now, the countervailing force is gravity pushing down, and atmospheric pressure essentially pushing down on this. And so the narrower the tube gets, actually, the steeper the meniscus. And when we have things like a beaker, we don't really notice the meniscus, but in a pipette, we really do, or even in a burette. And in this case, then the adhesive forces are slightly stronger than the cohesive forces. This phenomenon, capillary action, is super, super important. And the picture here is not really good, but these ones here are supposed to be narrower than those ones. And don't worry about this 2R stuff. But where capillary action, you might have seen it if you've ever had a finger prick test for like a blood test or something, if testing your blood iron, they give you a little prick and then they take a glass tube and the blood goes right up it. And that's, again, it's a narrow tube, and so the water climbs up easily. Now, the other place where this is incredibly important is in plants. So, you think about trees that are hundreds of feet tall, and they need to get water and nutrients up to their leaves at the very top. Plants don't have a heart to pump anything. But what they do have are very, very narrow tubes. And these are made up of what we might call they're made up of molecules like cellulose, which are basically big networks of sugar molecules. And sugar molecules have lots of oxygens and hydrogens stuck to oxygen sticking around. And they make these super narrow tubes. And through capillary action, the water molecules climb up these little capillaries in the tree and make it, hundreds of feet up in the air. All right. And so that's, again, how this works. Just as a sidebar, if you were ever to use lab equipment that's not made of glass, you don't observe a meniscus. So, for example, if you used burettes made of plastic, not very convenient, even if it's see-through, but there are situations where you have to, but there's no meniscus, right? So, for example, hydrofluoric acid, for example, hydrofluoric acid dissolves glass. So if you need to work with hydrofluoric acid in the lab, you need to use plastic glassware, lab equipment. And so if you were using, say, a pipette or a burette, there would be no meniscus. What I want to talk about now is what factors go into the formation of solutions. Why do some things dissolve in others, and what makes a solution form? So we're going to start with basically with covalent molecules and touch a little bit on ionic compounds at the end. So the first thing is conceptually, I want you to think about how solutions form. And you can imagine almost something a little bit like a Born-Haber cycle, but a lot simpler, and we're not doing any math related to it, all right? In the problem set, I think there's some math, and in these notes, there's some math, but this semester, we're leaving the math out of it. So if we want to make a solution, we have a solute and a solvent, and they have to combine with each other. Now, we have a solute, and something is holding the solute particles together. It could be ionic bonding, it could be intermolecular forces. And then we have a solvent that is also being held together, most likely by intermolecular forces. Now, basically, the way we imagine this is whatever's holding the solute together, those interactions have to be broken. And then whatever's holding the solvent together, those interactions have to be broken. And then we have to combine them and form new interactions. And the energy of these new interactions has to be generally, at least, greater than the energy of the old ones, more or less. Now, we're used to thinking in terms of enthalpy when we're talking about energy. Up until now, when we did Born-Haber cycles, or when we talked about, and Hess's law, or any other problems, we've often talked about, even in kinetics last semester, mostly we talked about enthalpies. But there are two parts to understanding whether a chemical process occurs. The first one is enthalpy, but the other one is entropy, delta S, right? And natural systems generally tend towards more disorder. Entropy is a measure of disorder in a system, and natural systems generally tend towards disorder. That's why, for example, your room never cleans itself. Mine doesn't anyway. That's more disordered. Or, it's why heat, for example, dissipates, because having heat confined in a small space. So let's say I have a pot of boiling water and I stick a metal spoon in it, right? It's not only the end of the spoon in the water that gets hot, right? The heat dissipates the length of the metal spoon because that is less ordered. It's more disordered than having the heat confined in one place. Similarly, a solution is more disordered than these two things separate. And you can think of just look at the possible combinations of particles here. Here we have really particles with themselves. Now we have all these different possible arrangements of particles that is more disordered. And so the real measure of whether or not a chemical process, including solvation or dissolving, occurs is based not on only the enthalpy, but on what we call the Gibbs free energy, delta G. And delta H minus T delta S. Now, again, this is really to inform you because I think the concept of free energy is really important. We're not going to really be doing any math. Not really. We aren't going to be doing any math related to this. Enthalpy of a system is negative. When the delta G is negative, a reaction is spontaneous, or a process is spontaneous. When positive, is spontaneous, and you can see, you think about it, normally when a system is hotter, for example, chemical reactions go faster, or when something is hot, it's easier to dissolve things in it, right? I don't know how many of you are tea or coffee drinkers, but if you take a tea bag and put it in cold water, it doesn't work very well. Or coffee, if you take coffee grinds and put them in cold water, also not a fantastic way to make coffee, unless you're making cold press, but it takes really, really long, like 8 hours to make cold press. So that's a whole other thing. Anyway, so here, when temperature goes up, the entropy component goes up. And so then a process is more likely to be spontaneous. This is just kind of an aside on entropy and free energy for you guys. But the idea that we're trying to get to the basis of is, how do we judge whether or not things are going to dissolve in a given solvent or not? And the thing that I want you to keep in mind, the rule of thumb is like dissolves like. And I don't mean, and what I do mean is compounds that can form similar intermolecular forces will be miscible or soluble. They'll be able to mix. So for example, the first case here, we have two hydrocarbons, heptane and pentane. And heptane only forms dispersion interactions with itself. When we have just pure heptane, the only thing it does is dispersion. Same for pentane. So when they meet each other, well, normally the forces that they form alone are dispersion. And when they mix, dispersion. So the two sets of forces are kind of the same, so great, they'll mix. If we look at something like acetone and chloroform, both of these are polar, so they'll probably mix. Water and ethanol, well, both of them can do hydrogen bonding, so they mix. But for example, if I tried to mix water and pentane, they won't. And the reason is water molecules are going to want to form hydrogen bonds with themselves, right? And they are unable to form a strong enough interaction to compete with that with, say, something like pentane. So, for example, here we have, say, water and oil. So this would be like salad dressing. I don't know why it's in a martini glass, but there you go. So oils are typically non-polar molecules. And so the water molecules here are more likely to form strong interactions with other water molecules than to form dispersion interactions with oil molecules. So they don't make like interactions, similar interactions, so they don't mix. That's why, if you have salad dressing, you shake it up and then it's okay, but then eventually they separate. All right. Some compounds can help bridge this gap. So I'll give you some examples, like soaps, for example. Just as a sidebar here. All right. So soaps are typically, they are often sulfate salts. So soaps will have, say, not silicon, sulfur. Let's call it something like this, right? And you usually have a counter ion of some sort. You might see things, if you read the ingredients on soaps or shampoos, you might see things like sodium laureth sulfate. And laureth is like an old word. It refers to a certain length of carbon chain. I can't remember, 16, I think, carbons long. I can't remember exactly what it is. But essentially what happens is this part of the molecule is ionic and polar. So it can form ion-dipole interactions with water. And then this part of the molecule here is carbon and hydrogen, so it's not polar. And so other stuff is miscible with this. And then when you rinse with water, it drags everything away. That's just a bit of a sidebar. Now, an example of this is, say, vitamins. So different vitamins vitamins can be, in one way you can categorize them is whether they are water soluble or fat soluble. So some vitamins, like vitamin C, for example, are water soluble, and you can judge that really based on something like, if we look at the structure, we see, I've got all these OHs, so the H is attached to the O. I've got an oxygen sticking out here, more OHs. So this molecule is very polar, also lots of opportunity for hydrogen bonding. So it's easy for water molecules to surround this molecule and dissolve it. So remember, in order for something to dissolve, it has to be solvated, right? And the word in the case of water is the water molecule, the compound has to be hydrated. But if we want water molecules to surround something else, well, it's got to be able to form strong enough intermolecular forces with the solute to compete with hydrogen bonding with other water molecules. So here we've got all this stuff all around it where water can attach by hydrogen bonding and surround it. So something like vitamin C is soluble in water. If we look at something like vitamin A, there is an OH sticking out at the end there. So conceivably, this molecule can hydrogen bond with water. But just at that end, there's nothing in the rest of the molecule that's going to encourage water to form any sort of interactions, right? This whole bit is completely nonpolar. And so what happens is it can only form dispersion interactions. Water is not going to make any dispersion interactions here. Water is going to be more likely to hydrogen bond with other water molecules. And so vitamin A is not soluble in water. It's a fat-soluble vitamin. The same is true for vitamin K, where it's nonpolar because these two dipoles cancel each other out, and the bulk of the molecule is nonpolar. Vitamin B5, you can see there's NHs and OHs sticking out everywhere. And so this one also is soluble in water. So the idea is you want to have a match in IMFs between the solute and the solvent. And if that's the case, then we're likely to see a solution form. They're likely to be miscible. So we're going to talk very conceptually about the energetics of solution formation. All right. There are some questions and slides where there's some numbers, but we're really not going to talk about those. Now, the solution formation here is basically, and we talked about this very briefly at the beginning, well, there's something holding the solvent molecules together. Let's assume it's water. And so that's hydrogen bonding. Then there's something holding the solute particles to each other. And then those have to be overcome and counterbalanced by whatever new interactions are formed. And in the case of covalent compounds, and water, we're looking at hydrogen bonding versus whatever other intermolecular force there is. In the case of, say, ionic compounds, we're looking at a slightly different situation, right? So the way we look at this is, we might call this the delta H of the solute, whatever's holding it together. This would be the delta H of the solvent. And this we could call maybe the delta H of solution, sometimes called delta H of mixing. That's actually not the delta H of, sorry. I hate this. Sorry, it's not delta H of solution. It's the delta H of mixing. And the delta H of solution then is whether or not the process is endothermic or exothermic. But this leaves out the entropy part of this. So the delta H of solution is a combination of this variation in forces. This doesn't entirely tell us whether or not a solution will form because, it doesn't take into account the entropy. Now, for ionic compounds, I apologize, I screwed up the boxes here. But if we think about what holds, so the delta H of solute, well, for ionic compounds, the thing that holds them together is the lattice energy. And then the solvent is we have to break hydrogen bonds and form ion dipole interactions. And we put those two terms together and call it the delta H of hydration. So how much energy is released when water surrounds it, and what are the factors that go into it. So we can imagine something like this, right? If we have Kf and we're trying to dissolve it, we have to overcome the lattice energy, and then we get some energy back from hydration, because hydration, remember, here we're breaking bonds and here we're making bonds. And when we break bonds, that's an endothermic process. We have to put energy in. And when we make bonds, it's an exothermic process. Now, this doesn't necessarily mean that Kf isn't soluble in water, because this is a very small amount of energy, and the entropy part of this probably overcomes it, and it's also temperature dependent. Now, just a reminder of ion-dipole interactions. So the strength of the ion-dipole interactions between each ion is referred to as the enthalpy of hydration. And so if we're just going to be qualitative about this, how do we judge enthalpies of hydration? How do we compare them? So there are two parts to this, all right? So the first thing is the size of the ion, all right? And again, this actually, the factors affecting delta H of hydration come back to this once again. So smaller ions have more exothermic enthalpies of hydration. What does that mean? It means smaller ions form stronger interactions with water molecules because guess what? The charges are closer together. All right. So we can see with these halide ions, as we go from fluoride to iodide, so iodide is significantly larger than fluoride. As we go from fluoride to iodide, the enthalpy of hydration becomes less exothermic. Right? And the other one has to do with ion size. So all these three ions are on the other side, the magnesium, lithium, and aluminum, they're all about the same size. And but as the charge on the ion gets bigger, the enthalpy of hydration also gets more exothermic. I don't want to say bigger, but more exothermic because, again, the attraction between the ion and the water molecule is higher. And so what does that mean? I think if we're trying to judge something like solubility, we are going to see small and highly charged ions maybe have a chance at forming stronger enthalpies of hydration. But we also know that small, highly charged ions have strong lattice energy. So where does the balancing act come into play? Right. So it turns out, and we don't need to know the math on this, but lattice energy is proportional to 1 over r, and hydration is 1 over r squared. That is not the important thing. What I actually want you to pay attention are these two factors that I'm going to talk about. The first one is ionic character. Now, what does that even mean? Because it's not something we have discussed very much. But if you think back to when we started talking about covalent bonding and how it was different from ionic bonding, I showed you sort of a line where we compared the type of the bond relative to the difference in electronegativity, right? And that if there's very small difference in electronegativity, then the bond is covalent, purely covalent. If the difference is a little bigger, it's sort of polar covalent. And then if the difference is greater than 2, we consider it to be ionic. But there's this kind of gray zone, right, where compounds that we would think are ionic, but the difference in electronegativity is less than 2. And what happens is those compounds are